In this video, I'd like to share how you could create an exponential model from a set of data. So in this case, we have some population data from different years. And because the year numbers are a little arbitrary in a sense, let me just take the decade number as the input, as the x coordinate. The advantage of that is that the values involved in the model will then be a little bit smaller, and we can kind of, what we're doing is we're taking 1900 as sort of a base year, which is maybe a little more meaningful based on this population data than the year zero. Now, a second thing I can do is create a graph of the data. So if I highlight these two columns and choose Insert, and then choose a chart, I'd like to create a line chart like the one shown here. So this chart is curving upward in a way that suggests an exponential type curve. So I'd like to add an exponential trend line to the chart. So I'm going to choose trend line and choose an exponential trend line. So we can see that the exponential curve that best matches the data is not fitting precisely to the curve, but it's giving a model that kind of connects with that curved trend. Let me choose more options, because what I'd like to do is actually see what that formula is. So I can choose to display the equation on the chart. But of course I want my chart not to be linear as it is now, I want it to be exponential. So I can see a couple things. In particular, I see the initial value at 1900 would be predicted to be 39,732. And the growth rate, it's a little hard to see there, but the growth rate is 0.0263, which would represent about 2.6% per year continuous growth rate. So let me extend our analysis just a bit to try to see that connection between the data and the exponential function that we found. Exponential functions are special because the percentage change is constant. And so these data points are evenly spaced, they're 20 years apart. And so I can find the percentage rate by typing in a formula. Equals tells Excel that it's starting a formula. I want it to be a percentage value, so I'm going to multiply by 100, and then I'm going to take the new value minus the old value divided by the old value. And so this will give me the percentage rate between those first two cells of about 45, 46%, and I can copy this downward by highlighting a bit of that column and hitting Control D to copy the formula into those lower cells. So this can be illustrative of what we're seeing here. So one thing to notice is that these percentages are representing 20 years of growth. So if I divide these numbers by 20, we'll see something that represents a little bit more. It's not actually the best way to calculate this, but we'll see something that represents a little bit more the growth rate for 1 year. And so what you notice, if I do a Control D again and copy those formulas down, the growth rate is actually not constant in the data. And so representing it with an exponential is something we can try to do. It's certainly along the lines of an exponential growth, but we're not seeing a constant growth rate, which is the characteristic, a key characteristic of exponential functions. The growth rate is actually speeding up. And that's why we see the data curve outpacing the exponential model.